Okay, now this problem involves a combination of resistor, inductor, and capacitor in series and in parallel. The voltage source here is 10 volts. It doesn't have a frequency because, as you can see, the capacitive reactance is already expressed in terms of kilo ohms, and the inductive reactances are already expressed also in kilo ohms. So it's no longer necessary to determine the angular frequency because of this. So which makes our life a bit easier. So the first thing that we need to do, okay, is to combine these three circuit elements that are parallel to each other. And in order to do that, we need to so let's write it down here. Combine XL1, XL2, and R2. In order to do that, we need to take the reciprocals of each of these and then combine them, which means that we need to take the conductive reactance, conductivity. We need to take the conductance G2, which is 1 over R2. We need to take the inductive susceptance BL1, which is 1 over XL1, and the second inductive susceptance, which is BL2, is equal to 1 over XL2. Okay, and from there we can already get the admittance, the equivalent admittance, which you call in this case as Y1. So Y1 is equal to G2 minus BL1 plus BL2 J hat. And we have a minus sign here because the taking the reciprocals means that J becomes 1 over J becomes negative J. Okay, so when we do that, again, you can do that in MATLAB if you wish. So we have 0.100 millisiemens minus 0.300 millisiemens J. So that's our Y1. Okay, and in order to combine that with R1 and XC, we need to take the reciprocal of Y1. So the next step is to take Z1, okay, which is the reciprocal of Y1. Okay, and we already know how to do this. We need to get the absolute value of Y1, and we also need to get the phase angle of Y1. Okay, and Z1 will give us 1 kilo ohm and plus 3 kilo ohms J hat. Okay, now that we've done that, okay, we can then combine that with R1 and XC. So combine R1, XC, and Z1. Okay, so this will give us our total impedance, the equivalent impedance. Okay, this is then equal to R1 minus XCJ hat. Okay, why is that a minus sign? Recall that Z is equal to R plus XL minus XCJ. And that is why we have a minus sign there. And then simply we add this with Z1. So Z total will give us 4.3 kilo ohms plus 2 kilo ohms J hat. Okay, just for completion, we can write it like this: XC is equal to 1 over C. Oh, but we already know XC. Okay, so now that we've combined everything, okay, so this is now our Z total. Okay, we can get the amplitude of the Z total, of course, and that's 4.74 kilo ohms. You can also get the phase angle, and that's 24.9 degrees. Okay, now in this case, we won't draw the phasor diagram, but instead, let's try to solve for the values of the voltages across each circuit element and the currents across each circuit element. We know that R1 and XC are in series, and that is also in series with Z1, which is the reciprocal of Y1. Okay, so this means that Z1, R1, and XC are or have the same currents. So solve for current IR1 and the current IC, okay, which will also give us the current across Z1. Okay, now how do we do that? Well, very simply, I is equal to 10 volts divided by Z total. Okay, and by doing that, we get 2.1 milliamperes. Okay, which means that the current across R1 is equal to the current across C, which is 2.1 milliamperes, and this is the current across the impedance, the equivalent impedance Z1. Okay, so that's the current through here, and here just before it reaches the junction. Now that 2.1 milliamperes will be distributed along these lines, and that's what we're going to compute, solve for next. So what about voltages? Voltages across R1, XC, and Z1. Okay, so the voltages, okay, so VR1, VC, and VZ1. So the voltage across R1 is just equal to the current that we have computed, and the resistance, which is 3.3 kilo ohms, and that gives us 6.96 volts. The voltage across the capacitor is 2.1 milliamperes times 1 kilo ohm. This will give us 2.11 volts. And the voltage across Z1 is equal to 2.1 milliamperes times 3.16 kilo ohms, which is 6.67 volts. Okay, how do we get 3.16 kilo ohms? Well, we simply take the absolute value of Z1, and that will give us 3.16 kilo ohms. Okay. Okay, so notice that it doesn't add up to 10 volts. So it's not 10 volts. And why is that? Remember that we're dealing with phasors, so this is not the correct way to check if you have the correct answer. The correct way is to solve this by taking the sum of the squares. So VR1 squared plus VC squared plus VZ1 squared. And if you do that, you get around 9.9 volts. Okay, so that's approximate, and that's all just because of rounding off errors. Okay, now VZ1 is the voltage across the equivalent impedance Z1. But the equivalent impedance Z1 was obtained by taking the equivalent, or by taking XL1, XL2, and R2 in parallel, which means that the voltage across these elements here is the same as the voltage at Z1. So that's 6.67. So in other words, so voltage across L1, voltage across L2, and voltage across R2. So voltage across L1 is equal to voltage across L2, voltage across R2 is equal to voltage across Z1, which is 6.67 volts, because they are in parallel. Okay, and we can easily get the current then. So we can get the current through L1, L2, and across R2. So IL1 is equal to VZ1 over XL1, which is 6.67 volts divided by XL1, which is 5 kilo ohms. So this is 1.3 milliamperes. Then IL2 is equal to VZ1 divided by XL2. So 6.67 volts divided by XL2, which is 10 kilo ohms. So this is 0.67 milliamperes. Finally, the current across the resistor is VZ1 divided by R2, which is 6.67 volts, divided by R2, which is also 10 kilo ohms. So that's 0.67 milliamperes.